Welcome to Lecture 8 of ES 320. Today we're going to look at polymer crystallinity and what is meant by that, and then how we can predict that knowing what we do about various polymers. And we're also going to look at the glass transition and the melting temperatures of polymers and be able to predict trends in those two things based on what we know about polymers. So let's start by looking at polymer crystals. So obviously polymers can't form crystals in the same way that we were talking about crystals in ionic solids, right? So we're not going to get particular ions or particular atoms sitting on different sites, like different lattice sites or interstitial sites. But what we can get are regions within a polymer where the polymer chains are packed very closely and very regularly and are crystalline. So a couple of definitions to start with. We have a polymer, which we talked about last time as being a long molecule that's made up of these repeating mers. Most polymers, well, all polymers are at least a little bit amorphous. So amorphous are the regions where the polymers are randomly packed. That's the bowl of spaghetti that we were talking about, okay? There can also be crystalline regions within a polymer, and this is where the polymer chains are packed uniformly. What's interesting is for polymers, it doesn't matter how they're packed, only that they're packed uniformly. In an ionic solid, it really mattered that the chlorine was on the corners, all right? So, but for polymers, that's no longer true. All right, so most polymers are semicrystalline, which means they have regions that are amorphous and they have regions that are crystalline. And one of the interesting tasks we may have is to figure out how much of a given polymer is crystalline versus amorphous. A couple of comments. No polymer can be completely crystalline, but polymers can be completely amorphous, okay? So how do we figure out what percentage of the polymer is crystalline? Well, there's two ways we can look at it. One is based on volume, to say 50% of the volume of this polymer is crystalline, versus the weight, which would be to say 60% of the polymer is, the weight of the polymer is in the crystalline regions. They're based on the densities of the various phases. So rho S is the semicrystalline density that you would measure if you had a polymer that had both regions. Rho A is the amorphous density. So that would be if you had an amorphous version of that same polymer, what would its density be? And rho C is the crystalline density, which is theoretical, because you can't actually have a purely crystalline polymer to measure the density of, but you can figure it out, and we can look it up on tables. So using that, we can find either the volume percentage or the weight percentage. The weight percentage is always going to be bigger than the volume percentage because more of the weight of the entire polymer is in the crystalline areas because that's where they're packed more closely.